shear force. So what is the web reinforcement? Actually, web reinforcement mainly including the stir, the bending, or link reinforcement. Actually, bending reinforcement is part of the longitudinal reinforcement. Just at that point, it bend up. So this is the 4.1 public section by bending the force capital and failure mode. So we see under the action of the load, what type of failure mode will be induced by the shear force. So in order to facilitate the characteristic of the shear failure, often based on the beam without the Weber reinforcement. So you want to research, you want to see what the failure mode will be. Normally we will try to do the test to design beam. Firstly, we didn't put the Weber reinforcement inside. That means we don't use stir or bend up. We just use the longitudinal reinforcement, and then extend by the beam without Weber reinforcement to the beam width. So in the chapter 3, when we define this, we just consider this longitudinal reinforcement. Actually, in the real situation, of course, we got this stir inside, and also we got this, or sometimes we still got distribution reinforcement. And in this pair, if you see from the side view, you'll see sometimes they got this bend up reinforcement. So now we want to see what failure mode will induce by the shear force. So normally we design the test. We design a model of the beam. First we don't put this directly inside. We just put this longitudinal reinforcement inside to see if under the action of the load, what the failure mode will be. So we see beam without Weber reinforcement. Here the Weber reinforcement we said is mainly referred to the stirrup and the bend up or oblique reinforcement. So we see at this situation without Weber reinforcement, inclined crack the stress state before and after. So reinforcement of the concrete beam, symmetrical concentrated load. We got the two concentrated load here at C and the D point. In this part, CD section, actually there is no shear force. You know why? This section, if you got the simply supported beam, you got the C, D. So if you draw the shear force and the moment, the diagram of this beam. So finally we got this. For the moment, it's something like this. So in this CD section, the moment is constant. For the shear force is like this. So this one in this CD part, there is no shear force. Is it pure? We call it pure bending moment, bending section. Because this section, moment is constant. You see, why we got shear force? Just because if you cut the beam at this point, the force at both sides is not equal. You have to generate the shear force to make the balance of this force. So do you know how to calculate this moment and shear force of this whole beam? So this, suppose F equal to 100 Newton. Both of this 100 Newton and this diameter span is 10 meters and this is 2 meters. This is 2 meters. So can you draw the moment? Can you draw this value? How much is the moment and how much is the shear force? The concentric force F, both F equal to 100 Newton. The diameter span from this, suppose this A, this B, AC equal to 2 meters, DB equal to 2 meters. So CD is 6 meters. So you just calculate how much is the force, the moment, and how much is shear force. Calculate how much is it? You want to do this calculation, this moment, or you don't see this. Just tell you the force, the beam is like this. Ask you to draw the diagram of this moment and the shear force. How to draw it?
Semester we didn't understand this one. We taught this in material mechanics, but no one understood it. We were taught in the last year by our theoretic mechanic, but no one understood it. They didn't understand.
So you understand, but I think it's easy to calculate.
That's what the lecturer said, but no one understood.
So now if I ask you to do this, can you get the result?
I don't really understand, but I know that there is force, there is spin, there is ruler.
Actually, we have to calculate the momentum at A. We have to calculate the resistance of B and AB, or calculate the momentum.
So, have you, the structural mechanics, have you finished or that's the slide now?
Because we were in this one, the classes we didn't study.
So we try to show this thing. The span is 10 meters. The action point C and D, the distance to the supporting point is 2 meters. So if you want to draw the moment, the diagram of the moment, so the first way, yes, we should calculate the reaction force at the supporting point. Is it? So because this two force is symmetrical from the span, so the reaction force RA and RB actually should be equal to I and RB, the vertical reaction force. So actually that means equal to 100 Newton. Is that? Because RA plus RB should be equal to F1 plus F2. Make this in the vertical direction, the force is balanced. Then, if we calculate, if we got this, suppose any point in this section, AC section, suppose this, the distance is x from this point. So if we want to calculate the moment at this point, normally suppose we cut at this point, and then at A point the reaction force 100 Newton, and the arm to this point is x, so 100 multiply x. This is the force in this arm. And you see, if you take it out here, we got A RA here, and this point we calculate the moment at this point. So at this section, you see, because C is this here, in this section beam. Is there any other force besides the reaction force A?
Yes, the one going in the opposite anti-clockwise.
Yeah, is there any other force here? In this section, you see that the supporting point, we got the reaction force going up. And if you want to make this part balance, you need to got another force going down to make this balance of this shape. So actually at the cut section, this force
It's going
down should be the shear force. You see, in AC section, no matter this point as which section, as long as it's not far away at CD, if it is in AC section, this shear force always equal to 100. Is it? Because I should equal to this shear force, this force balance. So at any point between AC, the shear force should be constant. It's 100. So this is the balance of the force and balance of the moment. In this AC section, between AC section at any point, if we draw the moment to this cutting point, so the reaction force, the arm is x, so 100 x is the moment generated by this force. In order to balance this moment, at the cut section, you have to got another moment to keep the balance of this structure. So that means this cut section, you also got the moment. The moment should equal to 100 multiplied x. So that means with the x getting greater, the moment is getting greater. So actually, you see, the relationship is just the moment increase with the increase of the x. So it's the proportional. So for the moment, if you draw the moment in AC section, it's a straight line increase, and when it's reached C, it's reached the largest 200, because it's 2 meters, 102 meters. So we draw the shear force. So for the shear force at the AC part is constant equal to 100. So if the point is in CD part, suppose at any position it is CD, so that means you see, suppose this point is here. At C point, suppose this point C, you got one force F1 here, 100. And then you got another reaction force 100 here. You see, for this part, you got reaction force going up. And you also got at this C point outer load, the concentrated force going down.
Yeah.
So these two forces actually keep the balance. So that means at this section, the shear force, you don't need any shear force. If you generate shear force, the structure cannot keep balance. So for the shear force, in the CD section, actually it is 0. So we see the moment. At the CD section, the moment, any position here, calculating the moment, because 100, suppose this is 2 meters, suppose the x is here, so the moment generated by the reaction force should be this one. 100, the R is x plus 2, because AC equal to 2 meters. So the moment induced by the concentrated force, F1, because the moment induced by the reaction force A is the clockwise, and the induced by the concentrated force is the anti-clockwise. So M1, M2 should be, because we see it's also 100 plus x. Is it?
But actually, if it is going anti-clockwise, won't it affect it, like negate it?
Yes, it's negative.
Yeah.
Yeah. Then, in order to keep the balance, then should be, we have this section, we should also got another moment anti-clockwise to keep the balance. Because of course, the moment induced by the reaction force is larger than this one. Because the value, the force is all 100, but the arm, this one is larger than this one, 2 meters longer. So this M should be M1 minus M2. Actually, you see, M1 is equal to 100x plus 200. M2 is 100x. Then actually M equal to 200. So in CD part, any position, just the change of x, but the change of x have no influence on this moment. So that means in CD action, the moment is constant. Is it? So this is the CD section. We see in DB section. Actually, DB section is just like an AC section. Just draw this, see? You should go. The shear force is in direction and different direction. This is going down, this is going up. So that's the diagram of the moment, the shear force. So you see, in CD section, the shear force is 0. The moment is constant. So actually, it's very easy. So first, to find the reaction force, and just use this balance the force and balance the moment to calculate each section the moment of the shear force. Especially for this simply supported beam, it's so easy.
Need more practice.
So finally, we see we got this moment, diagram moment, and the shear force. So you see the figure, but you should know how we got this figure. So you see CD part, CD segment, we call it the poor bending section. Because in CD section there is no shear force, only moment, we call it poor bending section. And the AC segment and the BB, this two part, is a shear curve section. Because in this part, not only moment but also shear force. So, under the load of the moment and the shear force, we can got the stress of the sigma and tau. It's different stress. So you know this equation. Do you remember? Sigma equal to m/0 divided by I. You know these two equations?
They are familiar.
This is the in the material mechanics. This the stress. This is the shear stress. So by this two equation, we can got this. We can got this two different stress.
Tensile stress and compressive stress.
Principal tensile stress and compression stress. Actually, this sigma is the included not only the tensile, also maybe represent the compression stress. Actually, tau represents the shear stress. Shear stress, see, for a section, in current section, this stress sigma is the compression stress, or in this direction, tensile stress. But the shear stress is parallel to this section because it's induced by the shear force. So tau is this direction parallel to your section, but the sigma is a what call is it? The direction is perpendicular to your section. The shear force is parallel to your section. And for sigma is sometimes maybe it's a compression stress or sometimes it's tensile stress, depending on your it's in tension zone or compression zone. So besides this sigma and tau, actually we see in the material scanning mechanics we know there's another stress is the principal stress. This means at this section, if you cut a small part of the structure, and by the analysis you find in this oblique section, you can got this principal stress. At this section, only the sigma stress, there's no shear force stress. I remember we call it the principal stress. How to call it? Principal stress or something stress. It should be principal stress. Remember it's there. And the angle, the direction, angle is normally, this is half normally equal to 45 degrees. So if you see, suppose this is the beam. If you draw at the end position, you draw the principal direction, this principal stress direction. You finally you'll find the principal tensile stress and principal compressive stress is the distribution is like this. It's like this. This picture shows the simply supported beam without web reinforcement. The raw, the two symmetrical concentrated loads. Induce this here. In CD section, you see it's only moment. There is no shear force. Because there is no shear force, the stress is you see the stress is all perpendicular to your section. In low part is the tension and the up part is the compression, but it's all just perpendicular to your section. It's parallel to your span. If you say at any position, if you cut this beam, because this section, all this stress is just perpendicular to your section. Because in this part, CD part, there's no shear force. At the end, as AC part or BD part, this section, it not only got the compression or tension stress, you also got this shear stress. Finally, under the action of this compression or tension stress and the shear stress, we finally got this principal stress is in this direction. So this is the compression direction. This line is the principal tension stress. So the principal tension stress is along this direction. Merely the 45 degrees, but from here it's greatly increased. Now at this position is nearly 45. Of course it's going up, becomes larger. So this is the distribution of the principal stress. Those one is the principal compression stress. Those lines is the principal tensile stress. So tensile stress just like this. That means once this tensile stress larger, the tensile stress is larger than the tensile strength of the concrete. That means it will generate a crack along this line, see, because the force is this direction. Of course, the crack is in this direction. If you pull this direction, then the crack is in the vertical direction. So because your tensor force is this direction, of course your crack will be at this direction. So understand? Because if you pull along this direction, of course if you generate the crack, it's along this direction.
So if you pull it, the crack will be from like the A prime to the B. When the crack is generated, it will be from the A prime, like from that part, the down part to that.
Yeah, from this point to this point, this direction.
So the compression.
Yeah, because you see, the crack normally is concentrate perpendicular to your pulling stress. If you draw this direction, the crack is this direction. So this line is the tensor force. So the crack is normally in this direction.
Compression too.
Yeah. So also you see this line is the principal compression force. So that means if this load is too large, the mean compression force is transferred in this direction. That means if this beam was crashed, so this part is in mean compression, because the mean compression force is transferred in this direction. So this part of concrete will be crashed. So in this beam, the concentrated force is in this direction. The distribution of the compressive force is transferred in this direction. That means in the middle part here, actually there is no. Of course, it has some, but the mean compressive force is go this way. You see, this figure is the content of your material mechanics. I think you should have studied. So if you draw a small part of the beam, you take out a small part of the beam, you got this compression stress, I got the shear stress tau, and the action of this the compression stress and the shear stress, you can go to the principal compression force and the principal tensor force is in this direction. You see, if you got this point, you got this compression force, you got this shear force. The product force should be like this, should be in this direction. See, you got this one point, you got the one roof, just pull this direction and pull this direction. The final action is go this way, just like this. So finally, the principal stress, principal tensor, principal compression force is in this 45 degrees. So how do you call this force? I don't know if it's a product force or. Yeah, because for this one the mass. Yeah. In the real situation, you pull this direction one force 1 and force 2. The result is going this way. So the real product force should be this direction. Of course, based on the value of the larger or not. If this value is equal, of course this is 45. if this F1 not F2, of course, is smaller than 45 degrees. So that's just like here. The compression stress and the shear stress, the product stress is in 45 degrees. So I rest. Okay, we continue to see this chapter 4. You see, we do this test for this simply supported beam with the total concentrated force, and in the middle part, this part, there's no Weber reinforcement. Here we see the Weber reinforcement merely refer to the stirrup and the planar or oblique reinforcement. So in this part, you see, under the action of these two concentrated force, actually CD part is merely is a pull bending part. There's no shear force actually in this CD part, only moment. So we draw the principal tension, this principal tension stress, this principal compression stress. We draw the distribution of this principal stress. We can got this curve. And here, if we take 3 small parts of the building for this beam, so part 1 is here, part 2 is here, part 3 is here. If we take smaller part of this beam out, see, this part 1 is at the neutral x. At this position, the tensile force and the compression force is equal, only for the shear force. So at part 2 is in the compression area. Part 3 actually is in the tensile area. So we got these 3 different parts. Part 1 in middle at the neutral x. So the compression or tension stress is 0. The shear force, we got the maximum value of shear force. The vertical force actually, the vertical stress. The horizontal stress, no matter compression or tension, is 0 because it's in the neutral x. Then we can get the principal stress is in this direction, 45 directions. And if at point 2 is a compression zone, this compression force make this principal tensile stress smaller. This compression stress, principal compression stress is greater. Then this direction, the angle is larger than 45 degrees. And if the point is in the lower part, in tension zone, in tension part, then this tension principal stress is larger than this compression stress. Then this angle is smaller than 45. So that's why the curve is like this. In the middle position, it's 45 degrees. At the lower part in the tension zone, the angle is smaller than 45 degrees. At the up part, the angle actually is larger than 45 degrees. So this is the there's a different position. This principal stress, no matter principal tensile stress. Now we see the angle of the tensile stress, principal tensile stress. The up part is the tensile stress. This is the principal tensile stress. You see, if we just extend to here, the angle, this part is angle is larger than 45, and this part, you see, if we take it to here, the angle is smaller than 45. Only at this middle point, the angle is 45 degrees. So under the action of this loading, because the internal force, we got the moment and the shear force. Once under this action, once the principal tensile stress larger than the tensile strength of the concrete, then the concrete of the generated crack, the crack generated. And also the crack is an oblique crack. The failure surface and the beam X bias. So that's the crack direction, you see. Mainly is the oblique direction. Basically is nearly 45 degrees. Because the principal tensile stress is in this direction. The tensile stress is this direction, then the crack should be this direction, perpendicular to the force directions. So, second section of the beam occurs, after diagonal crack occurs, the stress state cross section continue to change, and the stress redistribution occurs. So that means once the crack generated, once the crack occurred, the tensile force resisted by the concrete was transferred to the reinforcement. Then the stress of the reinforcement was increased greatly. Normally, once the concrete crack generated, we just neglect the tensile stress bear by the concrete. All the tensile force transferred to the reinforcement. So here that means the redistribution, the stress redistribution. The reinforcement stress increased greatly. Because at this stage, once the crack generated, this material, this concrete, this beam, reinforcement concrete beam, is no longer homogeneous beam. So some of the hook formulation, or some of the you cannot use to calculating the stress. So this is the incline, the mean diagonal incline crack. We take this part away, take this part along to see the balance condition of this to this beam. So this is the stress redistribution. Once this oblique crack generated, we see what different type of the stress we have. So first of all, the tensile force resisted by the reinforcement Ts, by the longitudinal reinforcement. This is the main part. And also, this longitudinal reinforcement can bear part of the shear force because it is a reinforcement, because it can bear some of the shear force. And also at the top, some part of the concrete remain uncracked. So at this part, the concrete resists the compressive force. So here we got this compressive force and also part of the shear force. And also along this crack, because the concrete can have some of the friction or butting force, just because it's not so smooth. Of course, it can just it cannot move because it got crack. These two parts should be have how to say the movement along this crack. But because this surface is not so smooth, of course we got the friction force like it's like the friction force of the bite of this crack, bite force or something like this. So this part force SA, so different force, and this section. So once this crack generated, we can see in the reinforcement, the stress of course increase, and also on the top and the compression zone, the compressive force also increase, because at the beginning the total section was maybe at least half of this section in compress, half of this section in tension. But once this crack generated, only this small part in compression, and all the tensor force transferred to the reinforcement. Oh shit. So wait a moment, we finish this part, because according to the schedule now we have break now.
No problem.
Because this is the office, the film from the office. They are thinking, oh, this guy, you are breaking.
Oh.
Doesn't matter, we finish this part.
Okay.
So the inclined crack appeared before the part for the angle cross section, longitudinal section of tensile stress. At the moment while maybe there's diagonal crack appears, the tensile stress in longitudinal reinforcement compression, inclined cracks. Oh shit, can you understand this sentence?
Should we read it?
Explain. You read this sentence, can you understand what's the meaning? Because this PPT is not mine.
Actually, read it.
I really sorry. This is too bad. This sentence, as you say, this sentence actually is not so clear. It's so confused. I can't even understand what they're talking about.
I should read it.
Okay, so the latest short break, we have according to the schedule, we should have half hour break, but the shear force is the main part, and also the tensile force resisted by the reinforcement. So this part is the main part. Along the crack, of course, we got this force as the friction, aggregate, or bite force. But this force is very difficult to calculation, and also the value is relatively small. So during the calculation, normally we just neglect this force. The main force we consider is this force, the tensile force, and also the compression force and the shear force at this position. Also, the reinforcement can bear some part of the shear force, or we call it the force longitudinal reinforcement VD. This force actually, this VD is also compared to the shear force here is not so large, and also this force is difficult to get the exact value. For simple, normally we just neglect this force and neglect this force. So for the balance, feel the balance. The balance in x direction, balance in y direction. Balance in x direction is the TS, and here the compression force here, and the y direction in this direction V and VC here, and moment just this force. So neglect this VD and the SA this force. Make it simple. because this force actually see along the crack. Is no theory to calculate this force. Once the crack generates these two parts of concrete, then the crack of course is not smooth, and the friction force, the bite force. So how to calculate this force? It's so difficult. This force is not actually this force is it's just a small part. So we just neglect it, make it simple. And so finally, once the crack generated, the beam is working like this. It works like the arch structure. See, divided into three parts: part 1, part 2, part 3, and the reinforcement. Reinforcement working as the rod. The rod, this reinforcement is just like the tie rod of the arch. And this part 1 is the main part. So this part 1 is the main part of the arch. The cross section minimum stress. So I think it's better to see in your figure, in your textbook, this figure. We also got this figure 4 to 3. Arch analogy. You see the stress state of the piece acid beam without web reinforcement is similar to the tied arch structure. This reinforcement is working as the tied of the arc. So what's the tied arc is it? It's just like this. It's one arch. Normally we see arches like this, we got the supporting point here. But sometimes we got one half of the arch. It's like this. It's not like this, it's something like this. Because the tied beam here. And the supporting is just like the beam is a vertical support. It's not in this direction. Normally for the rim of the arch is the supporting point is in this oblique section. But if you use the tied arch, you can use this vertical supporting system. So now this beam without a web reinforcement, once the crack generates, it works like this. The reinforcement works like the this tied beam of the arch. And this rim part, this concrete, works like this rim of the arch. So the system, the force system for this beam without the web reinforcement, it works like this tied arch. So we see the failure mode of this beam without the web reinforcement. Here we use the one of the parameter m. This m equal to moment divided by shear force and h0 effective height. So in our book we also got this we call it the shear span ratio. The shear span ratio, the definition is dimensionless. The calculation equation use this, where m and v respectively mean the moment and the shear force, and h0 is the effective height of this section. So why we define this parameter? Why we define this shear span ratio? Because different shear span ratio M will induce different of the failure mode of this oblique section. So normally in our book we told two types of different shear span ratio. Got one of the generalized shear span ratio and also got another narrow span ratio. Narrow span ratio M equal to A divided by H0. See what's the difference? A actually that's here means A equal to M divided by V shear force. So A is this distance from this force to the supporting point, the distance of this. Actually, we say moment. Moment actually equal to force multiply the arms. So that means A is the arm of the shear force. Shear force V multiply A equal to L. So now sometimes we use this A divided by H0 to calculate this span ratio. Basically, we use this. Basically, it should be M divided by VH0. But we can simply make it simple. We can use this, the distance of A divided by effective height to calculate this span ratio, shear span ratio. So for this failure mode, for this beam without a Weber reinforcement, normally we can got these three different types of failure mode. From this figure, you see, for this figure, the action point of the force to the supporting point, you see, the distance is longer. And for this part, the distance is getting smaller, and this one getting more shorter. So different value. So just now we see the narrow meaning of this shear span ratio equal to A divided by H0. Now you see this situation A is the longest one. The middle one is smaller, and this one is more smaller. So you see different action point or different value of A, the distance between the force and the supporting point will induce the different failure mode. You see, this once the action point to the supporting point is very near, the crack is concentrated in this very narrow oblique section, and all the crack is concentrated in this area. And for this, you see, the crack is distributed along this part. Also, finally, we go to the mean diagonal crack. And this one, actually, the crack is, compared with this, the crack is relatively smaller. And also, directly, finally, is got a mean diagonal crack. For this part, the concrete was merely, you just can imagine, is in comparison. The concrete is, the crack is just induced by the crash of the concrete. But this part, some of the crack is induced by the crash, some induced by the tensile. But this one is mainly induced by the tensile force. This crack is generated by the tensile force. Because we know the principal tensile force is like this direction. So all the crack is just because of the tensile stress, rather than the tensile strength of the concrete in the crack generating. So this different action point induce the different failure mode. But all these three different parts of failure mode belong to the brittle failure mode. Is appeared suddenly and we have brittle and tight or two different filament.
Plastic.
Plastic. So all these three filaments belong to this brittle one. It's appeared suddenly. Yeah. Once it's appeared, you have no time to just to repair or to just strengthen it. So we see this, reduce this. For this, the distance A very larger. This solution, if we calculate M, the shear ratio with the large A, we got this value. Normally we find is once it is less than 3. Once the larger than 3, M larger than 3, we got this type of filament. Generally occur in this relatively large shear span, M larger than 3. That means this A is relatively long, divided by this H0. Because we know H0 normally is from here to here. Once this distance is 3 times H0, it's having like this. So when the inclined crack appeared, and soon form a major diagonal crack, critical inclined crack, and a rapid development leading to the shear failure crack. And quickly it extended to the loading point. Just quickly to this point. Suddenly, generally quickly, diagonal pulled off for the beam into 2 parts. Just the tensor, mainly because of the tensor force. Failure surface then the net no crash neck. While the longitudinal reinforcement level, the tear production is often accompanied by a crack. The damage is the cable stay damage. So the shear capacity, this is mainly due to the destruction of the principal tensile stress, exceeding the tensile strength of concrete. So the beam shear capacity is very low. Failure load is equal to or slightly above the mean diagonal crack appear in the load. So understand what's the mean of this? Because this type of failure mode, just because the tensile force is larger than the tensile strength of the concrete. So the shear capacity of this type of failure is mainly dependent on the tensile strength of the concrete. Because once the tensile force is larger than tensile strength of the concrete, things will crack will generate quickly and they fail. So mainly depend on this tensile strength of the concrete. It belongs to the brittle failure. And this is the second. When this M, the shear strain ratio M, larger than 1, smaller than 3, so the distance getting smaller, a little bit smaller. So it's the brittle, the failure mode is like this. The bending beam shear diagonal crack appear in section. With the loading increase, cracks start to appear and a few oblique, one of which developed into a critical diagonal crack. So there are few of the crack generated, but one of these quickly just become the mean crack, diagonal crack. This critical diagonal crack appears. And it can continue to increase loading, beam. Diagonal crack extends to the load deep until the diagonal crack to the top of the concrete in the normal stress and the shear stress to be crushed under the action of the destruction. The damage is called shear press damage. Shear press damage. So at this part, not only because of the tensor, but also because of the compression force. So this type of the failure mood, the shear capacity merely concerned with the concrete strength, shear strength, or its disruption than the state high. So what's the meaning of this? So this next, I'm not sure if it's clear or not, but we can see your book, 82 page. You see the second shear compression is a shear compression failure. Actually, this second failure mode is we can call it the shear compression failure. The spread ratio, the shear spread ratio is between 1 and 3. So with the increase of the load, several diagonal crack coming into being, and one of them developing into the critical inclined sac crack. After the periods of the critical inclined crack, the beam still works until the concrete at the top of the crack is eventually crushed. So the shear capacity is related to the size of the cross section, the concrete strength, and the space and the strength of stirrup. Space and the strength of stirrup. So it's a little bit
confusing.
This book is a little bit clearer than this here. So and I also don't know what's this meaning. It's really bad. Maybe we can use this one. This the compound PPT I have made. You see this one?
Yeah, that's it.
So we see the third one. See this is the three different failure modes. Diagonal splitting, shear compression failure, and this. Well, just now we talked about this. Now the last one, diagonal compression failure. Once the action point near the supporting point, you see, you can just imagine the limit state, the force is move this point, just in compression. So once action for this area is the m smaller than 1, that means this distance is smaller than h0 in this part is mainly induced by the compression failure. The concrete is a compressed part. So for these three different failure modes, so which one do you think have a little bit stronger resist or loading carry capacity for these three different modes?
The last one.
The last one.
Splits and failure.
So because the last one is mainly based on the compressed stress of the concrete. So the compression, the last one, diagonal compression failure, the loading capacity is larger, the largest. And the middle one, shear compression failure. See, because not only shear but also compress. And the first one, splitting, is based on the tensile strength of the concrete. So we know that for the concrete, it's have a relatively low tensile strength, but very high compression strength. So the loading characteristic of this three modes is this one. Compressing, diagonal compressing is larger, shear compressing is a little bit smaller, and the slating, diagonal slating is the smallest, the loading characteristic. So it's based on, depending on the size of the cross-section, the concrete strength. So we see this film is we got from this test, because in this test, in the beam, in this side, we didn't put web reinforcement inside. That means we don't use the stirrup, or we don't use the bend up or oblique reinforcement. So this situation is not the shear force or the oblique resistance force is not strong enough. So the RC beam, reinforcement concrete beam without the web reinforcement is not convenient for this real use. So actually in this CHBC code, we have made requirement. You have to use, for the design beam, you have to use stirrup. Because stirrup is very helpful to the bearing of the shear force, to resist bear force. So shear force. So sometimes the web reinforcement is needed. The web reinforcement can effectively improve the shear capacity of the inclined section. That's the function. The web reinforcement can effectively provide the shear capacity of the inclined section. So there are 2 points. First one is the inclined section. Because in chapter 3, we just began the normal section or vertical section. Chapter 4, we mainly talk about this inclined section. And here is the shear capacity. In chapter 3, the T-shape or the rectangular shape, we are talking about the bending moment, the loading capacity. Chapter 4, we're talking about the shear capacity, resist the shear force. So the effect of web reinforcement. After the diagonal crack, once the diagonal crack appears, web reinforcement will greatly enhance the capacity of the beam, in particular the rod stirrup. So in this case, we don't put the web reinforcement inside. Once the crack generates, the beam will fall, will just collapse. But if you put the stirrup inside, then the filament will not belong to brittle one. Because you got the stirrup inside, you got the bending up reinforcement. Then the filament will working just like the plastic mode.
So it wouldn't be so sudden.
Yeah.
But you should put the stirrups.
Stirrups. Yeah. Stirrups have the very good function to resist the shear force in inclined section. So filament similar to this beam without a web reinforcement. RC beam with web reinforcement have 3 major filament of the diagonal section. The experiment study indicated that the major factors that affect the shear capacity of the diagonal section are shear span ratio. This is the most important one. Shear span ratio M. And the strength of concrete. Longitudinal steel ratio and stirrup ratio, the strength of stirrup. So we see first the shear span ratio, we have said, you can see from this figure, this the X, horizontal X is M. Once M is smaller than 1, normally the filament is belong to the diagonal compressing force. Compressing filament. Once M is in 1, 2, 3, normally it's a shear compressing filament. Once M is larger than 3, it belongs to the diagonal splitting failure. influence the shear strength ratio M. And also the strength of the concrete. Strength of the concrete also have this or some influence. The ultimate diagonal cross-section strength increased with the tensile strength of the concrete, and the relation is nearly linear. So what's this mean? The ultimate diagonal section strength increases with the tensile strength of the concrete. So you say it's the tensile strength of concrete. With the weight of the concrete increase, the tensile strength normally increase. So the tensile strength increase, that means the diagonal crack appeared will push pound.
Yes.
So that means that the barrier loading capacity is increased. So this is the strength of the concrete. Also, another factor is the longitudinal steel ratio. Longitudinal steel ratio in the beam in the bottom, the ratio of the longitudinal reinforcement. Of course, this you have stronger reinforcement inside. For not this reinforcement. Of course, we design normally for the normal section to bear the bending moment, but also it can bear some of the shear force in this oblique section. So the tested results show that ultimate diagonal section strength increases slightly with the increase of the longitudinal steel ratio, and the relation is nearly linear. It also increases with this reinforcement ratio. Actually, the strength of concrete, the tensile concrete, also the reinforcement ratio is, I think it's 80 handstand. So the stirrup ratio and the strength of the stirrup, we have called this the stirrup, are very useful, a very good function to improve the capacity resistance, the shear force. So, and otherwise, the equal equation, the ultimate cell strength tend to increase with the value of the yielding strength and the stirrup ratio. And the relation is nearly linear. The stirrup ratio is given by this. You see, area of the stirrup, and B is the width of the rectangular section of the web. So SV is the spacing of the stirrup in the direction of the longitudinal reinforcement. A is the total area of the stirrup within the stirrup spacing. Because the stirrup is normally, this is a circle, along, but along this longitudinal reinforcement, we know the distance between the stirrup normally not larger than 200 millimeters. So the reinforcement ratio of stirrup, ESV, suppose you cut at this distance, you have those stirrup, and you got this section, the area, this cut area of the stirrup. You got this area of this stirrup. And B is the width of the beam. SV should be like this, the space of this stirrup. So that's the reinforcement ratio for stirrup, how to calculate it. So for this chapter 4, we said that we are mainly talking about the design calculation with this calculation shear capacity. For this calculation, the mainly calculation base is based on this shear compression failure mode. That means it's M smaller than 3. This situation. For the calculation, we design the stirrup based on this situation. Once M too small or once M too large, the stirrup, the function of stirrup is not fully used. Normally we aim at this situation M larger than smaller than 3 to do the design. So when we calculate the shear force in this inclined section, the force we need to consider is here. We see shear strength of concrete, the remaining part of concrete. We see shear strength of the stirrup. All the stirrup resist the shear force, and shear strength of the bend up. This some of the longitudinal reinforcement bend up to resist the shear force. Finally, we got this basic formula. So this formula actually, what we see is semi-empirical, semi-theoretical, because in this actually we have neglected some force, some of the the friction force and the weight force induced by this. I don't remember. You remember not? See this. SA or VD, we all just neglected, make it simple. So here we see it's a semi-empirical and semi-theory. We just keep this VC, VSV, VSB here. We see this part, VSV is the force resisted by the stirrup, and the VSB, the force resisted by the bend up reinforcement. These 3 parts for the shear force. So, and finally we can put this VC and VSV together because VCS. So what VC and VSV, you see, VC and VSV. Because this is in vertical direction, but the VSB is in oblique direction, so you need to just decompose. Because see here is use the same theta. So finally, we can use this equation to calculate VU. VU is merely equal to this 3 part. So this 3 part you can use this equation to calculation. You see this the last part is ASB sin theta. This is the bending by the shear force bending by the bend up reinforcement. And this former part is this VSC. By VC and the stirrup. So how you got this equation? How this equation is semi-empirical and semi-theory. So there's no why. It just based on the experiment experience and some of the balance of the basic theoretical. So finally we got these equations. And then the meaning of this symbol A1, after 1, 2, 3, we have got some introduced in your book. Where is this introduced? Yes, in your book, 85 page. Your time? See you. We have break.
Okay.
Break. See how your time.
Dada Cyprien.
So the difference for this two, the difference for this samples is this formal part, this two part is the vertical direction. This third part actually is in this oblique direction. We need to do the decompose for this force. So finally we got this shape force Vu equal to F1, 2, 3, and this equation. So for this equation, see your book on your 95 page. What's the meaning of this?
95.
95. Oh, no, 85, sorry, 85. 85. You see, for F1 is the opposite sign influence coefficient of bending moment. So what's this mean? F1 is the opposite sign influence coefficient of the bending moment. How to understand this meaning? You see, they got a different value. For simply supported beam and continuous supported beam, near edge support, F1 equal to 1. For continuous beam and cantilever beam near intermediate support, F1 equal to 0.9. So divided into these two different situations. So R2 is a coefficient for the use of the pre-stress. For reinforcement concrete is equal to 1. For pre-stress equal to 1.25. Why pre-stress this value is larger, 1.25? That means 25% improved.
I think that is because of the steel.
Pre-stress. Pre-stress actually is a compressed force to the structure, to the concrete. We know the concrete, the compressed strength of the concrete. Just in one, say we have introduced the complete force condition. If imposing compression, just how to say. For the concrete field, steel tube. Remember, if the steel tube have a concrete field inside, the compressive strength of the concrete actually is improved greatly because they have concentrated around. Just like this. For this pre-stressed, R2 pre-stressed. For this structure, if you use pre-stressed, that means the concrete actually have a pre-crash. Then the compression strength of concrete will be compared with the normal concrete will increase. So here why we say for the pre-stressed structure, R2 equal to 1.25. For the reinforcement concrete, just 1.0. So that means 25% increased. Yeah, because that means the pre-stress structure has a stronger capacity to resist the shear force. So alpha 3 is the coefficient of the compressed flange. When the cross section has a compressed flange, alpha 3 equal to 1.1. So that means that the flange, if the flange is a compression, alpha 3 is 1.1. So B is the width for the rectangular section, or the web width for the T section or I section. H0 is the effective height, effective depth or effective height, that's we all know. And rho is the longitudinal slur ratio. So put it here, one thing we should pay attention is this P. P is also, we call it the reinforcement ratio, but here P equal to 100 rho, because rho is normally 0.0, maybe normally 1% or 2%, something like this. Now that means amplified 100 times.
Okay.
So this equation 2 plus 0.6 P. P is the reinforcement ratio, but it's 100 plus the real reinforcement ratio. So the real reinforcement ratio is 0.02. Now here is 2, because 100 times in this equation. And when this value larger than 2.5, if this larger than 2.5, say use 2.5. That's the regulation. FCUK is the standard value of the compression stress of concrete. And the rho SV is the stirrup ratio. FSV is the design value of the stirrup tensile strength. You see, what's the difference? FCUK is the standard value of compressive strength of the concrete. You see this appendix table. What's the design value? What's the standard value? They have a difference. Have a lot of difference actually. See what 317. The standard value and the design value, you see, for the same concrete, 317. Suppose we see concrete C30. Standard value for the actually compressed is 20.1. For the design value is only 13.8.
Now see which table?
1 to 1. Table 1 to 1.
1 to 1.
Table 1 to 1. 317. 317. You see the difference? So in this equation, you see, in this equation they have said this FCUK is the standard value of compressive strength. of the concrete. And FSV is the design value of the tensile strength of the bend-up bar or the tensile strength of this stirrup. So it's a design value or the standard value is different.
Okay.
FCUK is the standard value, it's not the design value. So this is the difference. No, because most time we use design value. Very rare chance we use the standard value. Yeah, but not here. They use this FCUK. They say they use the standard value.
Oh, she said, can you repeat? Can you repeat again?
I mean, when normally lots of things we use the design value. But here, FCUK is used the standard value. It's not the design value of the concrete. You remember we do the homework.
Yeah, we have FCD.
You also use the design value.
But here we use nowadays.
Yeah, in this equation, FCUK is the standard value. Because this equation actually is based on experiment experience. So why? You see why? No why? Just we based on so many experience, so many experiments. They find here we use this value is good. So that's the graph. Just remember this. And the ASB is the total area of the stirrup within the cross section. And theta x is the inclination of the bend-up bars tangent to the member x. Because this part shear force is in this direction, you need to decompose it to horizontal and vertical. For the shear force, of course, we use the vertical part. You need to decompose this force. Then in this equation, we got the sin theta. So that means this is the bend-up force. Bend-up force. The force in the bend-up is the reinforcement in this direction, but our shear force in this direction. So we need to got this thing. We need to just decompose this force. F plus sin theta is this. So in this equation we got this sin theta here. We got to find the vertical force to resist the shear force, because the mean force in the bend-up is actually is type of tensile force. You need to decompose this tensile force into vertical shear force to this horizontal tensile force. So in this equation we got this FCB sigma ASB sin theta. Because this equation we use the shear force. So that's why we got this. So this is the basic equation we need to calculate the surface, the shear force. So in our book, introduce these things: boundary of the shear strength of the beam, upper limit and lower limit. These two limits. Upper limit value of the shear strength. This value is depending on the dimension of the section and the compression strength of the concrete. The recommended up limiting value for the ultimate diagonal section resistance to prevent beam from the diagonal compression failure. when the dimension of the section is too small and the principal stress is too large, the size of the cross section should meet this requirement. See, in this equation, overlay distance BH0, you need to make sure BH0 plus this, make this requirement. So that means your section cannot be too small. If too small, you cannot got enough shear force. So this is the upper limit value of the shear strength. And the lower limit value of the shear strength. According to CHBC, if the inequality is right, it shows the principal tensile stress is too small to bring diagonal splitting failure. The standard configure according to the detailed requirement is like this. This is the equation in our book 425A. You see this value of the coefficients. In this equation, FTE is the design value of the concrete tensile strength, and alpha 2 equal to 1.0 for reinforced concrete is the same alpha 2, same as this equation alpha 2. For pre-stress is 1.25. Here alpha 2 is 1.0 for reinforcement concrete. For the plate structure, is a similar equation like this. So for this, from this equation, this is the lower limit value for the shear strength. This strength, if the dimension meets this requirement, then this beam will not failure like the slitting failure. Because I'm not sure if I'm clear or not. See, we got these three different failure modes. This failure mode is a splitting failure mode. So at this situation, the strength, the shear strength is relatively low because it's depending on the tensile strength of the concrete. And for this situation, it's relatively high. The incline section, the load bearing capacity. So for the design of this inclined section, we normally use this based on this failure mode. All the equation, this equation is based on the shear compression failure mode. So this two upper limit is to prevent your structure failure like the compression failure mode. And this lower limit is prevent your structure failure like the splitting failure mode. So by this limit, your design finally if failure is like the shear compression failure mode in the middle one. Because this equation is based on this failure mode. It's not suitable for the splitting failure mode or the compression failure mode. It's suitable for the shear compression failure mode. So we make this limit, upper limit and the lower limit to make your section, your design between this, or just if it's failure just looks like the shear compression failure mode in the middle one, just like this one. Just like this one. Not this one or not this one. So we see the basic calculation method. Calculation method. Primary design of the Weber reinforcement for simply supported beam with the constant height. So the data L square B H FCDN SD and FV FSV AS W0VD, all this thing if we know, then we need to design the neighborhood Weber reinforcement. So for this question, this condition is given conditions, and this unknown condition, unknown question, we need to calculate the neighborhood Weber reinforcement. So how to do this? See, the first step, check whether the section size meets the requirement or not. Just this upper limit or lower limit. Only meet these two limits, we can use the equation to calculation. So first to check this is the upper limit. Otherwise, if this doesn't meet the requirement, then otherwise we increase the section size or increase the concrete strength. And check whether the Weber reinforcement must be determined by calculation. So use this. Otherwise, Weber reinforcement must be determined by the calculation. So this one is this equation. If it meets this equation, then we have to calculation. If this was not satisfied, what that means? Check whether the Weber reinforcement must be determined by calculation or not.
If it doesn't satisfy the rule.
If this satisfies,
meaning we have to continue to calculate.
yeah. In CTBC, the maximum shear force is in the section of the support. Of course, we know near to the supporting point, the shear force is the largest one. So the burden of the concrete slab cannot be less than 60%. So 60%, at least 60% of shear force was bearing by the slab and the concrete. And another, not more than 40% is bearing by the bend up or oblique reinforcement. So why 60%? This based on experience or experiment. So now, so this third step is calculating the exact value. Because once you got this value, VU, then you can go to this 60% and 40% for the this 60% for the concrete and the slab, and 40% for this bend up bar. Then you can get the exact value for this different reinforcement, slab and the bend up. Then the fourth step, we design the slab. So design the slab. Normally, we normally preset the diameter and number of the slab. The number means the 2 or 4 lines, because we know we have different type of slab. This is 2 lines, and also sometimes we got this 4 lines. So at the first beginning, you should determine use 10 or 11 or something. What type of reinforcement do you use? And then you determine it's 2 lines or 4 lines, what type of slab you use. And then we can use this equation to calculate the space, because this slab is 1 circle, 1 circle, 1 circle. But how how large or what's the distance between each stirrup, you need to calculation. That's what we need to design calculation and determine. So use this equation S V equal to R1, R3, and this all this. I think all in this equation everything is known. R1, R2, R3 we have introduced just now. And FCUK we know the standard way with the concrete. FSV the design way with the stirrup, the reinforcement for the stirrup. And the ASV the section area of the stirrups. And BH0 C, gamma 0 VD. Gamma 0 VD is the external shear force induced by the external load. C, we know the relatively height, we know x divided by x0. So by this equation, we can go to SV, space of the stirrup. And also this you should meet the requirement. If you got this SV maybe equal to 300, normally it's not satisfied because normally we ask for the space no larger than 200 millimeters for the construction requirements. So the first step, we should calculate the bend up bar. We design the bend up. Not only stirrup, we also need to design bend up. So use this formula, ASBI equal to this. VSBI, this is the shear force resisted by this bend up force, bend up reinforcement. And this equation, you see FSD sin C, just like this. F sin C. You see, this equation, you move this part to here, that means F, the stress, and the area, and the C, and compression to this direction, and this is the coefficient, then equal to this force. So VSBI is from the CHBC. So this value, according to the HBC, CHBC is not larger than 40%. So the shear force of the first bend up rule, VSB1, we taking the 40% of the total shear force. And the shear force in the bend up point, which burden by the reinforcement is chosen to calculate the next H rule of the bend up. So that's what it means. Oh, I think we got this figure, see? Yeah, this figure. You see, for this first bend up reinforcement, the shear force is this bend up reinforcement to vary the shear force VSB1. This VSB1 equal to 40% of this shear force. And this, at the first bend up point, at this point, the shear force VSB2 is better by the second bend up shear force. Or we use this VSB2 to design this second bend up reinforcement. And same thing, this as the second bend up point, this shear force is used to design the third bend up reinforcement. So that means at this point we need to how much reinforcement we need to bring up depend on the shear force. How much shear force we need to resist to bearing. So for the first bend up reinforcement, you need to bearing 40% of the total shear force. And for the second bend up reinforcement, you need to bearing the shear force at this point. And the third one, you need to bear the shear force at the second bending up point. So this is the meaning. The shear force of the first bend up rho bar when SB equal to 40%. The shear force in the bend up point, which burden by the reinforcement, is chosen to calculate the next each rule of the bend up bar. The bend up angle of the bend up steel bar and the position relation normally is 45 degrees. The bend up angle of the bend up steel bar is normally 45 degrees typically used. And some specific condition, 30 degrees may also can use. By the way, normally we don't consider modern, we just use 45 degrees. Yeah. And the position relationship between the bending bar in a simple beam, the bending point of the bending up bar is the first rule in terms of the supporting on the central section of the support. And the bending point of the bending up bar in the next row should be on or beyond the before bending up section. So what's this meaning? So can you understand what this meaning? The bending point for the bending reinforcement in the next row should be on or beyond the before bending up section. So that means this is the first bending point. This is the second bending point. See, this point should be beyond at this side of this point. This section. This point should not in this section. Should at least at the bottom at this point or outside.
So it should be in line with the bottom of the.
Yeah. So this point, if you go up, it should be at the point at this left of this point. You cannot be right at this point.
It should be before the next one.
Yeah. So today we here. Next time we do some example, maybe more clear.
好的。